Swayam Prabha, free DTH channel for education.
Okay, we'll start. So what we are going to do in this Zoom session is we'll first go through whatever we have already discussed, like whichever I have shared with you guys in the last video, and then we will continue from there. So feel free to interrupt me anywhere if things are not clear, because it has a lot of intricacies. So it's quite normal that you might be missing something. So feel free to stop me there. Okay. I'll share my screen now and would show you the notes and we will discuss that. Hope my notes is visible to you guys, right?
Yes, sir.
Okay, good. So there are in fact three magnetic fields. If you look at MR imaging, we discussed one and we are going to discuss the second one here, and then there is a third magnetic field also there. What was the first magnetic field we discussed about in detail in the first two lectures?
B naught.
Right. It is the strong external magnetic field that you are going to apply on a given sample or a voxel or a whatever it is. And that field is B naught. So this picture tells you the story that is associated with this B naught. You take a sample or a voxel of size of the order m millimeters. Then there are a lot of protons there. So we are talking about the hydrogen atoms that are there within that sample. So each hydrogen atom now is oriented in its own direction, and we discussed about the properties of these protons. They have a charge, right? And they have a mass, and another very important property is also they have an angular momentum also. Okay, and that means it is rotating along its own axis, and this angular momentum would bring in a magnetic property to it. This angular momentum of that proton would make it act as a tiny magnet, very small magnet there. Now, within the sample, there are at a microscopic level, there are millions and millions of these atoms, but because they are all oriented in different directions, any moment you take the magnetic, the moment coming from each of those atoms would eventually will be summing up to zero. Now to bring some detectable, perceivable, tangible amount of magnetic field into it, what we are going to do now is you bring a motivational speaker here. Okay, that B naught is a very strong magnetic field that could bring polarization as well as, of course, the resonance in the sample. These are the two properties that this external B naught would be bringing in. So our normal intuition tells us that once you apply this, everything gets oriented in B naught. Okay, but the situation is not so simple. In fact, what would happen is roughly half of the protons, we call it as protons, although we are calling it as protons, we are talking about that isolated proton. Let's say you have C13, out of that 12 are having pairs, only one is there single. So that's only the proton we are talking about, not every proton. Although we loosely talk proton and hydrogen, these words interchangeably, you just make an understanding there that we are talking about the left alone proton in a nucleus. Okay, yeah, coming back. So what would happen there is roughly half of them gets oriented in parallel to the applied field, magnetic field, and the remaining half would be rotating or in the opposite anti-parallel state. That's the scenario. So this is what you could see here, and there would be few that are slightly giving more preference. There will be slightly more atoms or protons that got aligned with B naught, then thus bringing some faint detectable magnetic field here. That's the B naught story of B naught. So again, we have looked into the quantum mechanics also while looking at the properties of a single dipole. On the other hand, at a macroscopic level, while we are doing the analysis, we are doing it using classical physics or classical mechanics, right? So then we notice that this would be resonating overall. This would cause a value of, let's say, m, and then the next one is we want to, this is as far as in a way you could think that now it is kind of a magnet. Now you want to, the next step is to bring a change in the system where you would be applying now in the transverse direction. It is something that's rotating, okay, in the z direction constantly. There it is, there in the z direction. Now what you want to do it is you want to poke it now, so that you would see change of magnetic field, okay, and that eventually resulting in a detectable voltage signal as well. Okay, so till then this was the equation that we have derived in the previous Zoom session, where you call at a macroscopic level magnet, the whole magnetic field capital M bar is equivalent to the cross product of this M bar with B bar of T, and multiplied with gamma. So that's what we have done earlier. Now what it tells you is, now what you do is, this is in this z direction. Now you apply a magnetic field in the xy direction, okay, a magnetic pulse. This pulse frequency would be of RF frequency because that's where it resonates, okay. Anyways, when you apply this and you make it tip onto the xy plane, earlier it is on the z axis, now we want to make it tip onto the xy plane. That's the very idea of it, okay. So then the question is, once you tip it onto the xy plane, you remove this, then what is going to happen? Okay, so that's the basic scenario. The second one which you are applying is called as B1 magnetic field, okay, or the coil which is used for this purpose, since it would be of radio frequency. Why it will be at radio frequency will be clear here, we will come to that. So this coil through which you apply the secondary magnetic field, which we are referring to as B1, is referred to as radio frequency coil or RF coil. Okay, simply they will be calling it as a coil also. Earlier one is a magnet, they will call it. The second one is a coil. Then you will come back to later in the next class perhaps, where you want to modify the frequencies spatially. So that's the spatial encoding. For that, on top of B naught, you would be using some other magnetic fields that's called as gradient magnetic fields, and those are called that's also is another coil, gradient coil, but usually you refer to this as RF coil, that's as gradient coil, okay. Those are the three magnetic fields that are involved there. Now uh, what we are going to now see is, when you applied a field here, you made it tip onto that, then what's going to happen to this? Okay, what's the frequency at which it would be rotating? See, the moment there is an angular momentum, it keeps rotating, okay. It's like you put a force, there is an object, you keep an angular, at an angle you are applying a force, it is bound to rotate. But now what we are going to study is at what frequency is it going to rotate. So this is the signal. See, this expression is independent of the way B bar of T is there, okay. Earlier it is B naught, and now it is equally applied to a magnetic field that you are applying in the xy plane as well. So that if you look at it, you could see here dm bar by dt would, so initially you assume that this length of this is this m bar, is now completely in the xy plane. Okay, so that's m bar here. So the magnitude, let's call that as magnitude of m. Then at what rate it is rotating, how do you know? That would be equal to the rate of change is dm bar by dt. So this, for a small duration, if you consider, let's say you could say, but first you figure out how much time it takes for it. So what's the whole distance it has to travel, okay, to complete one rotation would be, that's essentially rotating along the xy plane in a locus of a forming a circle. So that you could say it as 2 pi times m bar. That's what it is. And then the rate at which it is rotating is, for example, here gamma times m bar times b bar. That's the magnitude, right? That's the magnitude of dm bar by dt. So if you take for 1 second, let's say this is the one, if you are making this is just for an intuition, although not a rigorously correct there. Okay, and then to cover 2 pi times magnitude of m bar, which should give you the time taken for one rotation there, right? Because it has to travel here on this locus for 2 pi m bar, circumference being 2 pi m bar. So that would tell you the time it takes for completing one rotation would be 2 pi over gamma times magnitude of b bar. And if you want the frequency in hertz in 1 by t, that would give you gamma by 2 pi into b bar. And if you want to say in terms of radians, that would be equal to gamma times b bar radians per second. 2 pi f would give you the radians. So it is now rotating. So for the time being, you are not worried about the z at this point. Okay, the magnetic field in the z direction. It's just you applied this, then what's going to happen to this m bar? Okay, that's what you are taking a look at here. So it is telling you that if you are applying a b1 in the xy plane, such that it is going to tip onto the xy plane, then this m bar would be rotating at an frequency of gamma by 2 pi times b bar. Okay, if you notice, even the frequency for E equal to h nu, the energy transactions at microscopic level that we derived, I think in the second class, there also you would have seen the same the frequency at which the each dipole resonates is also the same thing. And microscopically also, the resultant magnetic field also would be rotating at the same frequency. Clear so far?
So this rotation is caused by the applied magnetic field in the XY direction, right?
Yes, I would applied magnetic. See, earlier also it rotates, but again it's rotating around the z-axis, means it is there, just there itself. There is no change there. Now the angle, see, you made it. So I would say the precision is caused by B1. That would be a more precise statement.
Yes, it's the precision, right? Not the actual rotation around it.
Exactly. The precision is caused by the rotation. You could say it is caused by the B naught itself. But it is
Yes, okay.
precision that is caused by B1. That is perhaps a more precise.
Okay. So it will proceed until it aligns itself with the XY direction again.
See, what we did is, we are putting it slightly differently. We are applying this B1 until this tips onto the XY plane. See, if you are keeping it is like there is something rotating let's say in the Z axis. Okay, I am poking it. So I could poke it till any position. I could poke it, just come half the way and stop it. Then from there it would come back. Now the situation I am considering is I keep poking it till it comes to the XY plane. That's the B1 here.
Okay, okay.
That's why just the maximum value is there for in the MXY plane. The projection of your M bar, in other words, is maximum at that point where you have withdraw your B1 field.
Okay. So once we withdraw it, it again starts coming back in the
Exactly. That's
direction.
right.
Okay.
That's right. That's what we would now discuss. Because see, this pulling force is there. this magnetic field, whichever we have applied, that's always keeps pulling. Now another guy has come and he poked it in the XY plane. Now this you stopped, but this pulling is always there.
So is this force sufficient to tip it over? Like anyway, this transverse field that we're applying, it will have to struggle a bit, right? Because already there's stronger magnetic field in the z direction already.
Yeah. See, as you said rightly, that once this is there at resonant frequency, it makes it pull. It's if you want it in terms of some magnitudes, if it is in the order of Tesla, is your B naught. Okay, this a frequency of the order of micro Tesla is good enough here for B1. That's good enough to pull it, because that rotation will be still there. That is not lost. Just that it comes into a more stable state. That's it.
Okay, sir.
Yeah. Any other questions so far? Okay, then we'll see here. See, now you consider this rotating in the XY plane. Okay, for a moment, just consider this. Then if you place a coil in the XY plane, okay, what is this coil is? It's just the coil that you have used earlier for giving this RF pulse to bring it into the XY plane. Now, a rotating magnetic field here, you know from your Faraday's laws that this would generate, if you look at from this point, that it would again bring you a signal which oscillates at a frequency which has a frequency of the same omega naught, and that would create a signal here. This is what we are going to detect. Now, as we just now discussed, what would happen now is this pulling is there. The z direction anyway, you have this b naught. So what it would do now is it would try to this rotation itself now would be it could be rotating at the same frequency, but now it would again keep rotating and coming into the z axis finally. Okay, that's what would happen. So then there are two aspects that we would be in, particularly in MR imaging, we would be interested in. One is, usually you take the signal. One of them is you observe the signal here. How is it varying? So the projection of this, in other words, the projection of M bar, your magnetization vector, magnetic field vector on XY plane. And of course, another one you would be interested in to see is what would be, how is this its projection of M bar on the Z axis is varying. These are the two important aspects that we take look at. Now, it can be roughly approximated the way it comes back and restores its value. So what happened the moment it is on the MXY plane? What is the component of this M bar vector on the Z axis? What's the component? What is the projection of this M bar on the Z axis when you have tipped it onto the XY plane at that moment? That's a simple question, I guess. You tipped it onto the XY plane. What is its projection on the Z axis? Magnitude of that.
Zero.
That's all. It's zero, right? Then what would happen? It would gradually regain, okay, once you withdraw that, and it would finally come into the Z axis. Okay, so this to put it, you need to again look into both at a microscopic level also here. There is something called as spin lattice interactions that are going to happen if you are looking at a microscopic level. What it means is, see, it essentially went into a high energy state now by absorbing that, if you are looking from a quantum physics point of view. Now it now tries again to establish a thermal equilibrium state. So now these energy transactions again would happen, and it will settle down to the earlier low energy state. That's what would happen. And what can be approximated is that this decay, this regaining would happen exponentially with time. Okay, just like you have seen your equations of voltage across the capacitor or the current across an inductor, this equation should intuitively make sense to you. Mz is finally it should reach to m naught value at t equal to 0, the moment it is on the xy plane, that this mz equal to 0, and as it progresses it comes back to m naught. So is that equation intuitively okay for you? Mz is equal to m naught. So m naught is the magnitude of your m bar vector. Okay, m naught into 1 minus e to the power of minus t over t1. Okay, this is very similar to what you have seen in voltages and current equations for capacitors and inductors. Now, what is it that dictates this T1? Or there are essentially two parameters. One is the density of protons you have. Okay, if you recollect from the previous class, we have seen the equation for m bar under for a given b bar value. There is a term associated with the proton density, right? So that is one thing. Second thing is the amount of B naught you have applied. If you recollect, gamma times B naught is also the amount of energy you have. We have seen the energy barrier between n minus and n plus. So now those energy transactions has to happen for it to come back to the previous state. So higher the energy magnitudes of energy transactions, that has to magnitude of energy being high. Okay, that's what if your b bar is high, there you have gamma times b by 2, if I remember correctly. That's the energy del. So first class we have discussed, I think first or second class also we discussed. So if you look at there, delta we have written there, I think somewhere here. Yeah, so this is what h into so this is the frequency. So this delta E we have worked out. It happened to be h times gamma by 2 pi into b naught. In fact, this resonant frequency times h. Okay, that's nu is essentially this. So if you have a higher b naught, the amount of transactions that has to happen for coming from an anti-parallel high energy state to low energy state, the magnitude of those energy delta E is large, so it essentially takes more time. Okay, so these are the two factors that would decide how much time it takes, but eventually this is what would happen. Okay, now another thing we have done here is, you already, without considering this b1 field, this was the just b bar of t without considering this t1 relaxation. This is the equation we got. So this also we are trying to write dm bar by dt. Okay, if you notice in some of the textbooks, they started from here and they arrived at here. But again, for me, this is more intuitive. So I started from here and then I took a derivation. This also some people have followed this one, at least one I have come across, that they started here and came back here, which is more intuitive for me. So I did the same thing here. So dmz by dt, if you take, you could calculate what would be the derivative of the rate of change of magnetic moment. Clear so far? About this is called as t1 relaxation. Okay, this time, which time constant for, again, you remember that the xy plane is referred to as transverse plane, the z axis is referred to as longitudinal axis. Okay, so this you could see here, it is we are now looking at how the longitudinal relaxation is going to happen. So this is referred to as longitudinal relaxation. And in the lattice, there will be between, for example, you might be having a hydrogen molecule. Between hydrogen and hydrogen, these interactions of interchange of energies and everything would be happening there. So this is usually referred to as, from there the energy transactions would happen. So they refer to it as spin lattice interactions. That is the major reason. Again, this is just we are not going into much detail about the spin lattice as such, the chemistry part of it, but that's what essentially contributes to it. And I'm fine as long as this equation makes sense to you, that this again comes back and t1 is the time constant given there. Is it fine? And this t1 is referred to as spin lattice time constant. Okay, So the second one now. Here we are going to take a look at how the magnetic field is going to change on the XY plane. Okay, the first idea would be, okay, anyways, this projection of this M bar would be there. This is your Z axis. The moment it comes to the Z axis, obviously the XY, it is there aligning with the Z axis, your M bar vector. Its projection on XY plane is anyway zero. But interesting thing happens here is that is true, but even before that, your mxy, we call it as mxy, the projection of m bar on the xy plane becomes zero. Even before this would happen anyway, based on this time constant t1, okay, at t1 where this is equal, roughly equivalent to zero, that time it is anyway going to happen. But this transverse field becoming zero would become even before that. The reason being, each one might be rotating. You again, now we need to borrow from the quantum atomic level, now from the proton level. Each is rotating, but the moment the coherence between the phases of each of these individual dipoles is lost, okay, assume that this is still rotating at an angle, okay, but the starting points are different, the phases are different. So now one might be in this direction and another might be in this direction. You take its projection on the xy plane, so each would be opposing there. Okay, so because of the loss of coherence in phase between the individual uh, protons, okay, or you could say the atoms, or you could, much better word is the spins, they also call the same thing as spins. Loss of coherence between them is also referred to as, the word, technical word for this is dephasing. So they are in phase when things are, everything is fine, but the moment this whole phenomenon is happening, they get defaced, their phase in, they will be rotating at resonant frequency, but still the starting point where it is starting, say for example, one thing could start here and another thing might start at a different location, okay, still they might be rotating at the resonant frequency. Now you take the projections of it, suppose one is there like this, rotating like this way, okay, both are rotating around the z-axis with the same angle, but if the starting points are different, you just draw a diagram. What would happen there? Suppose if I have the starting point of one is like this and another is like this, you compute the mxy, obviously they will be opposite and become zero. Similarly, the sum of all millions of atoms or protons that are there for which you are taking the projection, then this value is going to be small there, and that's going to die down much faster than regaining of the magnetic field vector along the z-axis. So this is referred to as transverse relaxation. And now initially, since we considered that this has been tipped onto the xy plane, so that's where its value is maximum. Again, I'm starting from the magnetization vector and going back to writing the derivative of this angular moment, rate of change of the angular momentum, sorry, magnetic momentum there. Okay, so m naught into e power minus t over t2, this is called as spin time constant, because this between the spins this dephasing is happening, and that's making it on one way, this moving to z axis obviously would reduce its projection onto the xy plane, that is anyway there. But even before this projection becomes zero, because of this dephasing, despite this being at an angle with z axis, still this already the transverse magnetization would become zero. Okay, so this value, so this t2 time constant is much smaller. It would be usually of the order of some milliseconds, whereas the other one could go up to some order of seconds there, the t1 time constant it takes for regaining. Clear so far? This is a very important thing, even if you, yeah, this is a good opportunity for you to learn these things. Otherwise, if you had to work on a some problem, you would normally will not get an opportunity to read all these things and know some this background about MR imaging, T1, T2 and everything. Is it clear? Any questions so far?
So the process of dephasing happens as soon as the RF signal is like removed, right?
Right. It gradually starts. The dephasing would gradually start. It's like the teacher has gone out. Slowly, the chaos starts. Okay, it builds up, and the rate at which it builds up is given by T2.
Okay, yes, sir.
Yeah. Any other question?
So this movement in the like movement of again going back into the longitudinal direction.
Ah,
So this thing, it's precessed actually, right? It does not go directly. It rotates and then again aligns itself in
it is.
longitudinal direction.
You mean it rotates and it comes this way? Yes.
Yeah, like that.
Correct. Correct.
Okay.
That's true.
So, but if this, like, if the anyway this transverse magnetic moment is going to zero early,
Hmm.
then we can't actually determine it, right? Like in any way,
We can
because
determine. You look at it because see, in fact, it is this one we make most use of it than the other MZ one. This transverse T2 one. See, you have the coil to recognize this, and the same coil you are using here. So that's what you could detect here. And again, what would happen? You will see a small appetizer for what you would see when it comes to spatial encoding is that you would focus on one region, you get the result, and then you move on to the other one. Okay. So further to happen also, you want things to happen fast. Then only you could move. This story should get complete here. Whatever excitation, everything, the field voltage you are getting should be done. You should be done here and should be moving to the other location where you are giving a different resonant frequency now to excite in that particular location. So in fact, you want this T1 and T2 to be small, not large. Even is that point clear?
yes, sir, that makes sense. But due to this phase desynchronization, which we can't actually measure, isn't T2 different every single time?
No, it doesn't really matter for a given proton density. Okay, for a given this would be the same value you would compute it. It's not, it doesn't so the average time it takes would remain same. Just like although each dipole is moving in its own direction, you could say given a proton density and applied magnetic field, you could say what would be the m naught value. In similar lines, you could say here for a that's what distinguishes the one tissue from the other, and it would be a characteristic of a tissue in fact. So that's what, if you notice here, for example, gray matter will have 100 milliseconds, white matter 92 milliseconds. This is the time constant. These are the time constants, so which is essentially dependent on the proton densities.
Okay, sir.
Good. Any other question? Okay, so then let's again take a look into yeah, this is an interesting and important graph here that is shown. Okay, just 1 minute. One minute. Yeah. So this is an important graph here. Notice here an important point that your T1 relaxation, which means bringing it back to the z-axis, would essentially or primarily dependent on two things. One is the applied magnetic field strength. As we discussed, the more the field strength, the magnitude of energy transactions that have to happen is more, so it takes more time. So on one side, these are for different tissues. You could see here, as the magnetic field strength increases, the time taken would also increase here. Second thing, the proton density. Okay, that's something which would dictate how the spin lattice interactions would happen. So it in fact does depend on the kind of material you have. So this is what tells you the T1 with varying magnetic field strengths, it increases, and also for different materials, how is it going to have. So these are the two things that dictate or govern how T1 would be there. You could also see here let's say some 100 milliseconds, at least it is there, more than 100 milliseconds here. You could, ignoring this, maybe this is 200 milliseconds, right? 0.2 seconds means. So from that, it's common, for example, if you are taking somewhere around 1.5 Tesla, okay, this could be, it could go to up to 1 second for relaxation. Again, they want to reduce these relaxation times also. So then what they do is, while doing, for example, some MRI of kidney, they will inject some agents that would speed up the process of this relaxation. So these timelines would come down. So for example, one such thing is gadolinium. They would be giving you the contrast agent of gadolinium, injecting them into your veins, and then they will take this MR scanning. So you would see shortly, for each location, for each voxel kind of stuff, or at least for each, depending on where you want to slice wise you want to do it, you want to repeat this whole process of applying your B1 multiple times. You have to apply your B1 field and then record the signal. Each one is one measurement in your Fourier domain. Okay, that take it for granted, the statement for now, which would eventually become clear to you. So for that matter, this is what actually makes the MR imaging very taking a lot of time. So to bring down the time for the whole process of your relaxation to happen fastly, they would use certain materials with contact of which this whole process, this spin lattice interactions will be speeded up. So for example, one such thing is gadolinium. That's what they would be using there. And then the second one is the relaxation happening in the transverse plane. You could see, although the movement into the towards the z axis is causing you, but before that, much faster, this is going to happen in the order of milliseconds. Okay, and thus this is not dependent as such on the magnetic field strengths. Okay, that's one thing. It's just dependent on the kind of material you have, the proton density. So these are, let's say, the values for it: gray matter, white matter, muscle, fat, kidney, and liver. Again, we could carefully dig in more detail, but I think for the time being, let's keep it at that level. So you could distinguish different, for if you are taking a measurement, let's say at this point, at some point of time, okay, let's say here at let's say 0.5 seconds or so, then knowing that field, kind of I could figure out what is the kind of material I have at that point. Okay, that's how I could figure it out. It's clear so far?
So the resonant frequencies are also independent of the applied magnetic field, right?
Correct. It's gamma times B naught, right? So it is dependent on the gyromagnetic ratio and also the magnetic field strength that you are applying.
So it does depend on the one that we apply.
You mean the B1?
It depends on B1 or B0.
It depends on B naught, because B naught is the main, it will be of the order of, let's say, 1.5 Tesla, and this B1 will be hardly equivalent to some micro Tesla. So you could say it is dependent on the B naught value.
Okay, sir.
Yeah, good. Okay, so the last point to mention here is what would happen now, the block equation. Okay, so people are pronouncing it, I think, not bloch. I was using bloch in my recording, but it looks like it should be a block. Okay, I'll from now on call it as block equation. Okay, for block equation is, you got this one, which is a reason of precision. Okay, dm bar by dt is equal to this cross product is something causing you the rotation, or you could say the precision. And then from the longitudinal relaxation, dmz by dt turns out to be this one. So that you add here, okay, that times this is there in the z cap, in the direction of the z axis, right? That's what how it is varying. So dm bar by dt, so in the z cap direction would come here, and similarly from here in the xy plane, the variation you could write, and that would give you mxy is nothing but, initially we are calling it as mxy, but now if you want, you could write it as mx into x cap plus my into y cap, components of it in x and y directions, by T2. So this is your block equation where the first term accounts for precision, the second term accounts for transverse relaxation, and the third term accounts for longitudinal relaxation. Okay, still we have it as a derivative of m bar. We have not solved it yet. That's what we would be doing in the next video lecture.
So the first term should be cross product, right?
Yeah, very good. Sorry, that was a mistake. M bar cross. Huh? I would correct that. Thanks for pointing it out. That's right. M bar cross should be there. Good. That's good. That's a mistake. Any other questions? I'll then stop the recording here.